Acids, bases, and pH. Shampoos contain a pH 5.5 buffer. pH 5.5 buffer. Because the human hair becomes rougher if it's exposed to alkaline conditions, therefore the biological buffer systems in our bodies ensuring the tissues at the right pH. Another useful buffer, biological washing powders contain buffers, keeping the pH at right level for enzymes to work efficiently. How a basic buffer is made? Made by mixing a weak base with one of its salts. The salt fully dissociates in solution, and the basic buffers have a pH greater than 7. How an acidic buffer is made? Made by mixing a weak acid with one of its salts. The salt fully dissociates into ions when it dissolves. The weak acid, so it's only slightly dissociates. So the salt fully dissociates into ions when it dissolves. However, the weak acid, so it only slightly dissociates. Acidic buffers have a pH less than 7. Definition of buffer: a solution that resists changes in pH when small amounts of acid/base are added or when it's diluted. Now, just memorizing this definition, you can really get a good understanding of buffers, right? Or key facts, right? Because it resists change. It doesn't actually stop pH from changing completely. It resists it. It only works when small amounts of acid/bases are added or when it's diluted. So that's why memorizing definitions are so important, because obviously you could get a definition question where it's just like define buffer for 2 marks, a buffer solution, or it's a question on it and you'd have to use your knowledge of the definition to apply it to the question. So a solution that resists changes in pH when small amounts of acid/base are added or when it's diluted. Buffer doesn't stop the pH from changing completely. It resists the change in pH. Definition of diprotic acid: one that can release 2 protons when in solution when it reacts with base neutralize. Release two protons when it's in solution. So a key fact about diprotic acids: when it reacts with a base neutralize in 2 stages, 2 protons are removed from acid separately, so 2 equivalence points. And you know, I can see, I don't know why, but like one marker and it'd be like, what kind of acid is this? And it'll just show you 2 equivalence points, so therefore it would be diprotic acid, show you the pH curve. State one key thing about using titration results to calculate concentration: we need to measure the neutralization volume as precisely as you can. Measure the neutralization volume as precisely as you can, aka to the nearest 0.05 centimeters cubed. We need an indicator that changes color exactly at the endpoint of the titration. It changes color over a narrow pH range and it lies entirely on the vertical part of the pH curve. Methyl orange color, phenolphthalein. It's red methyl orange at low pH. 3.1 to 4.4 is the approximate pH color change, and at high pH it's yellow. Phenolphthalein colorless at low pH. 8.3 to 10 approximate pH color change, pink at high pH. Strong acid/strong base titration, we can use both methyl orange, phenolphthalein. Strong acid/weak base titration, we can only use methyl orange. Weak acid/strong base titration, we can only use phenolphthalein. And weak acid/weak base titration, no indicator, as no sharp pH range, so none of them will have a narrow pH range that lies entirely in the vertical part of the pH curve. So here's all the graphs basically that you do need to memorize. So strong acid, strong base is like that. That's pH volume of base added. Strong acid/weak base is very similar to strong acid/strong base, but this bit's a bit longer, and obviously the vertical part of the curve is smaller, and it's just like that. Weak acid/strong base, where we start off around about pH 7, goes up here and here. That's pH volume of base added. And then weak acid/weak base, basically just drawing it like that. And you can see the equivalence point, it's not, you can't use any indicator for that. It's pH volume of base added. Now the opposite, strong base/strong acid, volume of acid, pH volume of acid added. The good thing about these four is just these flipped around, so it's just that way. Strong base/weak acid, instead of this way, it's just that way. Weak base/strong acid, and pH volume of acid added, volume of acid added, volume of acid added, volume of acid, whereas volume of base added for these ones. Same weak base/strong acid, just flip it there. And then volume of acid added, weak base/weak acid, same thing. And obviously you can't use indicator for that as well. You have to use a pH meter. So acid-base titration, we add a standard solution of acid to a measured quantity of base. Add a standard solution of acid to a measured quantity of base. Once you know the amount of acid to neutralize the base, we can work out the concentration of base. Add a standard solution of acid to a measured quantity of base. Once you know the amount of acid to neutralize the base, work out concentration of base. Now, all these formulas and all that. So pKa is minus log 10 Ka. Ka is 10 to the power minus pKa. Kw is concentration H plus times by concentration OH minus. Smaller the pKa, stronger the acid. That's really important. Strong base is fully ionized in water. Concentration H plus 10 to the power minus pH. pH is minus log 10 concentration H plus. Kw does changes as temperature changes. Ka is an equilibrium constant and it applies to a particular acid at a specific temperature regardless of the concentration. Acid dissociation constant applies to a particular acid at a specific temperature regardless of the concentration. Acid dissociation constant. Weak acid and weak bases dissociate slightly in aqueous solutions, so the concentration H plus isn't the same as the acid concentration. Set the two key assumptions for finding the Ka of a weak acid. Only a tiny amount of HA dissociates, so we assume the concentration HA aqueous at equilibrium is equivalent to the concentration HA aqueous at the start. And we also assume that dissociation of acid is greater than the dissociation of water, so concentration H plus aqueous is equivalent to concentration A minus aqueous. Strong diprotic acid, concentration H plus equals 2 times by concentration acid. Each molecule releases 2 protons when it dissociates. Strong monoprotic acid, concentration H plus equals concentration acid. Ionized fully in solution, each molecule releasing 1 proton when it dissociates. Bronsted-Lowry acids, proton donors. Bronsted-Lowry base, proton acceptors. The units of Kw always multiply 2 dm to the power minus 6. pH scale is a measure of hydrogen ion concentration. And smaller the pKa, stronger the acid, and that's really important to memorize. And for this part, where it's all the calculation questions or the formula, number one, memorize all the formulas and do loads of practice questions, past paper questions, because they always like to ask questions acids and bases.